Okay, recording is on. So here you go. It's going to be Guido Boccali. Hopefully I'm spelling that right. Bicategories of automata and automata in bicategories. Stage is yours. Okay,
thank you. I would like to thank the organizers and for the beautiful conference, and my co-authors Andrea Laretto, Foscolo Reggian, and Stefano Roneia. Today I'm talking about two different topics which are linked by this kind of rhetorical tool. We're talking about, the presentation is divided in two parts. One is called Bicategories of Automata, and the other is called Automata in Bicategories. The main link between the two parts is the fact that this is the first step in an overall overarching research project that we are dealing with. In this project, we are focusing on some old works, mainly from the late 70s and the early 80s, mainly by René Guitart and the French school, that focused on automata theory with heavy tool from two-dimensional category theory. And our work is to let those old pearls shine, because mainly because of the difficulty of the technical tools at the time of their at the time they were forgotten. And so we believe that these works should be seen, these ideas should shine nowadays. And so we are trying to do this. Let's start. I'm sorry, I cannot. Okay. Now, first thing first, we need to define a Mealy machine. Guitart himself defines a Mealy machine, a generalized Mealy machine in a categorical setting, to be a span of this form in a monoidal category K. Here we have a state object, in French it is état, a dynamic morphism from which take a state and an input and gives us a new state, and then an output map S, which gives us which takes an input and a state and gives us the output. Obviously, we can fixing one input object and one output object. We can define a category of Mealy machines of input I and output O. In the obvious way, we can a morphism between two such machines is a morphism between the state objects, and such that the obvious diagrams commute. Similarly, we can define a Moore machine, which is a Mealy machine mute with the S part mute in the input argument. And similarly, we can define also a category of Moore machines in the same way. Obviously, in most cases, the interesting monoidal structure is Cartesian. And in such cases, we can define a bicategory of Mealy machines. This definition was first found by Lavore-Gianola-Román-Sabadini-Walters in 1998. The bicategory of Mealy machines in K has as objects of K, as one cells, as one should expect from I to O, my Mealy machines from I to O, and as two cells, Mealy machine morphisms. Obviously, the rest of the data, such as composition of one cells and horizontal and vertical composition, is inherited from K itself. A conceptual construction of this bicategory was given by Katis-Sabadini-Walters in 1997. It is the category of pseudo-functors and lax transformations from the monoid of natural numbers and the suspension category of K, which is simply the monoidal category K seen as one object by category. Moreover, some years later, they found a universal property of this bicategory as the free category with feedbacks on K. Interestingly, Guitart came up with a very different notion of bicategory of machines. Here we are considering what is sketches as the bicategory of machines with input and output in categories. I have to say that his spelling of the definition is rather obscure, and so we had to reconstruct what we believe he had in mind. But nonetheless, the bicategory MAC-S, the one defined by Guitart, is this one. Zero cells are categories. One cells are span of this form where P is a discrete op vibration, and two cells are morphism of op vibration, i.e. op Cartesian functor, such that the obvious triangle commutes. Composition, as it happens in span, is defined with pullbacks. We need some machinery to assess some relation between the category defined by Katis and Sabadini and this bicategory defined by Guitart. So let me simply go through some lemmas. We have to notice first that the home categories of MAC AB fit into strict pullbacks in cut of in big cut, obviously, of this form. Also, we need to notice that if K has countable coproducts preserved by the tensor product, then the span of a Mealy machine can be extended to such a span as you can see here in the diagram, where E star is the free monoid defined by the infinite coproduct of the nth power of I, and D star and S star can be defined inductively from components Dn, Sn from this kind of type as you expect. Obviously, if K is also closed, the map D star corresponds under the monoidal closed adjunction to the monoid homomorphism E star from E star to the home EE. Now, we need also a definition that is given by Guitart that could seem rather ad hoc. This definition is that of fugal automaton. If we have two monoids, a Mealy machine of this form is called fugal if its S part satisfies this equation, which could be not very perspicuous at first sight. We have tried to motivate it in two ways. This condition is exactly equivalent to the possibility of defining a functor big sigma from the displayed category given by the category of elements of the action induced by this star to the monoid n, because the fugal condition gives us the possibility of preserving identities and composition. This said, this condition lets us produce a universal fugal Mealy machine given one of this form, as you can see there. And this construction is well behaved for one cell composition in Mealy set, in where set as the obvious Cartesian structure, in the sense that composition, two cells composition is functorial. We have encoded this data in this lemma, and so we have a fugal extension functor, which we will call flat, for each AB object of sets. We have this functor of this form. Now, we also have to notice that this diagram commutes for each category of this form. And a first result that we can produce is that we have a functor for each A and B, pi AB, from Mealy flat set A star B star to Mach S A star B star, given by the universal property of the home categories of Mach S, which was that one of the fullbacks. Now, the interesting thing is that when we compose these two functors, the fugal extension and pi, we have the action of on one cells of an entire functor gamma that goes from Mealy set to Mach S. Now, what is the meaning of this functor is that the fugal extension functor flat admits a right to a joint, while the functor pi identifies Mealy flat set as the one full and two full subcategory of Mach S spanned by monoids. So we found some kind of duality between bicategories of automatas with input and output in monoids in the sense of Guitart, and the notion of bicategory of machines given by Katis-Sabadini-Walters. Now, this is all for the first part, the part of bicategories of automatas. Now, we would like to introduce the notion of automatas in bicategories, because until this point we had defined Mealy machines inside a monoidal category, but as the motto says, a monoidal category is just a bicategory with a single zero cell. Then it is natural to ask whether these definitions that we have been given admit a generalization when instead of K, we consider a bicategory B with more than one object. This section answer in the positive. And also in this section, we will find some new notions that are seemingly undiscovered of morphism between automatas. This idea is not entirely new. It is partially inspired by a paper, really a note by Bainbridge from 1975, where the author models the state space of abstract machines as functor, of which one takes the left and right can extension along an input scheme. But that work was rather obscure and probably also quite ahead of their time. So we really prefer to get the general idea of the work and try to set that in a more general framework and state the results in a more modern language. So obviously, well, the definition of a Mealy machine in a bicategory generalizes pretty naturally. If we have one cell I from A to B and two cell O, one and another one cell O from X to Y, and two cells alpha and beta, we can form a span of this form, where obviously the composition plays the role that was played before by the tensor product, because when we specialize to the case of one object by category, we have the same definition. The important observation here is that the mere existence of the span forces the types of I, O, and E in such a way that I must be an endomorphism of an object A, and E and O have to have the same source and target, and the source has to be A. Interestingly, these assumptions are required even to consider an object like in the definition above, to make iterated composition such as I after I after I after I and so on, as meaningful as iterated tensor such as I tensor Y tensor I and so on. And in fact, the two concepts coincide when B is a single object. In the monoidal case, this fact was not clear because obviously every one cell is an endomorphism, and so we could not discover that. Now, we can define bicategory valued Mealy machines in this way. If we have a bicategory and we fix one cells I from A to A and O from A to B, we can define a category Mealy B IO as follows. Objects are diagrams of two cells as we have seen before, and morphisms are two cells that satisfy the obvious constraints that are simply generalization of the ones you said you saw before. Now, the category is really defined obviously, we can define also a bicategory of Moore machines in the same way. It is obvious. It could be useful to represent spans of Mealy machines in this kind of way, because we can give a conceptual motivation for the convoluted shape of finite products in Moore K IO and Mealy K IO that we have studied in another paper as scan extension. The terminal way of filling this kind of shaped diagrams can be characterized, as I was saying, as the right extension of the output object along a certain one cell obtained from the input I. To do so, we must first ask to the ambient Tom categories BAA that each of these admits a left adjoint to the forgetful functor from monads over A to the Om category itself. Obviously, this is asking for a free monad to be available whenever it is useful. Our claim is then that the terminal object of Moore B IO is obtained as the right extension in B of the output O along E natural. From the unit eta from the entity to E natural of the pre-monad on I, a canonical modification from the right extension along I to the run extension of the identity with components at O given by two cells and with sigma modification from a natural transformation between the right extension along E of O to O is a choice for the right leg of our span. From the multiplication of the free monad on I, there is this canonical modification here, whose components at O mate to a two-cell delta zero, such that the composite that you can find depicted here is the left leg for our span. Together, this data assemble into a bicategorical Mealy machine, and the universal property of the right-can extension says that it is determinal suction. A similar line of reasoning yields the same result for Mealy BIO, only that now sigma is the two cell obtained as the mate of this other composite from the counit of the adjunction given by the can extension property. In passing from Mealy K to Mealy B, we gain an additional degree of freedom by being able to index the category over pairs of 0 cells of B. And this is particularly interesting in the sense that the definition of Mealy BIO and its indexing over pairs of objects AB of K leads to a seemingly undiscovered way to define morphism between automatas. We call such a morphism intertwiners. If you consider two bicategorical Mealy machines of this form indexed on different bases, as you can notice, AB, we have here AB and A prime B prime. An intertwiner UV between the two consists of a pair of one cells U from A to A prime and V to B from B to B prime, and a tripole of two cells iota, epsilon, and omega, disposed as in the diagram below, such that the following diagrams commute. Interestingly, we can define two cells between intertwiners in the following way. If we have two parallel intertwiners between bicategorical Mealy machines, two cells phi psi between them consists of a pair of two cells phi from U to U prime and psi from V to V prime, such that these identities that you can see nicely depicted here hold true. What is we did not really found yet, at least, a real-life application of these intertwiners, but the fact that we discover this kind of morphism and the fact that we can give a definition of two cells for an arbitrary bicategory, and so even when in the case of a monoidal category, which is again just a single object bicategory, seems to us to be a result that was quite enough for presenting this definition and for future works. I have to thank in particular between my co-authors Andrea Laretto, because he formalized in Agda practically all the proofs that we managed to achieve in the presentation, and you can find them on our GitHub. I believe we do not have it here, we do not have the link, but I can send to anyone who is interested. Thank you, everyone.
Right, thank you very much. So are there any questions? Any questions? No one in the room, so maybe online? Anyone? Okay, also no questions, so maybe as well some questions might arise later on Zulip. Right, I mean, very well done. We're on time. I think in the first session it was like, oh, we were ahead of time and it's never going to happen again. So hey, it's happened again. Right, Nelson, you want to get ready?